In a previous video in this series on solving second-order differential equations, I showed you how to solve the homogeneous differential equation. That is, I showed you how to solve the differential equation of the form a d squared y on dx squared plus b dy on dx plus cy equal 0. In this video, we are going to look at the inhomogeneous case. In other words, we are going to look at the case in which this is equal to some function f of x, some function of x. How to find the solution to that equation. So, we recall that when we were looking at the homogeneous case, we talked about the auxiliary equation. We said that if you have, we talked about the auxiliary equation, and we said that if you have a d squared y on dx squared plus b dy dx plus cy equals 0, then you form the auxiliary equation am squared plus bm plus c equals 0. And this was the auxiliary equation, and we said you solve this equation, you get two values for m1 and m2. And we said if the values of m are real and distinct, then your solution to this equation, the general solution to this equation, will be a e raised to the power m1x plus b e raised to the power m2x. And if the solution to this equation, the roots are real and coincide with each other, this means you have two equal roots, then you have y equal a plus bx times e raised to the power mx, where m is just one of these roots, which is the repeated root. And we saw that you could move from here to get the case in which the roots are imaginary. In other words, you just put the e raised to the power ix and then you add the two. You see that it will give you a cos mx plus b sin mx. And if they are complex with a real and imaginary part, then you have e raised to the power the real part times x times a cos imaginary part x plus b sin imaginary part times x. We are now going to look at how to solve second-order differential equations for the inhomogeneous case. So we use the same procedure that we use for first-order differential equations. Remember, in one of our previous videos, we saw how to solve the inhomogeneous case for first-order differential equations. If you haven't watched that video, you can just click, you can go back and watch it before you continue here. So the procedure was this. First, we find the complementary function CF, and this is the general solution to the homogeneous case, which we have done already. Second, we find the particular integral pi, which is the particular solution to the full equation. And finally, we find the general solution by adding the complementary function and the particular integral together. If you have not seen how we found the complementary function and particular integral, you can go back and watch the video on complementary functions and particular integrals. Let's look at the steps again. Find the homogeneous equation and hence the complementary function. Choose a triad function and hence find the particular integral. Then find the general solution by adding the complementary function and the particular integral. Here you recall from the previous video that these are the steps in which we use to find particular integrals. If f of x is a constant, then the particular integral will just be a constant, and you have to look for that constant. If f of x is a linear function, then the particular integral is also a linear function. And if f of x is quadratic, you also have a quadratic particular integral. If it's an exponential function, then you should also have an exponential function. But if it is a trigonometric function, sine x or sine px or cos px, then you also have a trigonometric function for the particular integral, a cos px plus b sine px. Remember, if f has, say, sine 2x, then your p here is 2. So this should also be like a cos 2x plus b sine 2x. Remember, you will then have to differentiate y equal that. You differentiate it 2 times, substitute back in your equation, and look for a and b. Okay, so let's do an example. We're asked to solve this equation. So our f of x here is a constant. First, we write down the auxiliary equation for the homogeneous case. And then we solve the auxiliary equation, we get our values for m, and so our complementary function would be a e raised to the power negative 6x plus b e raised to the power 2x. And next, we have to find our particular integral. Since your f of x here is a constant, so your particular integral will also be some constant a, which we will look for. We differentiate a 2 times and then substitute back in this equation. When you differentiate y the first time, you get 0. Y prime will be 0, or dy dx will be 0, and d squared y over dx squared will be 0. So you have 0 plus 0 minus 12 times a should be equal to 18. And so your a should be negative 3 over 2. Therefore, your particular integral is y equal negative 3 over 2. And so your solution should be the complementary function plus the particular integral. So it will be this part plus that part. Second example, we're asked to solve this equation. First, we take out the homogeneous case. So we just let that be 0. And then we form our auxiliary equation, solve the auxiliary equation, and we get a repeated value for m. So our complementary function is y equal ax plus b times e raised to the power 2x. And then next, we guess a particular integral. And since this is a linear function, we also have to guess a particular integral that is linear. So we'll have to write y equal ax plus b. And then we differentiate y 2 times and substitute back in this equation. So when you differentiate the first time, you'll get y equal a. And you differentiate the second time, you'll get d squared y on dx squared equals 0. So this will be 0 minus 4a plus 4 times y equal that. And then next, we have to equate coefficients. You can see here that the coefficient of x in this on the left hand side is 4a, but the coefficient of x on the right hand side is 3. So 4a should be equal to 3, and the constant term on the left hand side should be 4b minus 4a, and the constant term on the right hand side is -5. So we'll get 4b minus 4a equal -5. So we solve these two equations for a and b. We get a as 3/4 and b as -1/2. So our particular integral will be 3/4x minus 1/2. And then our general solution will be the sum of the complementary function and the particular integral. Solve this equation. In this case, we are given boundary conditions. This means that we have to look for the two constants a and b. Here are our boundary conditions. First, we solve the homogeneous case. We look for the auxiliary equation, which is m squared plus 2m plus 5 equals 0. So m should be complex in this case. So if you remember, it means your complementary function should be e raised to the power real part times x times a cos imaginary part x plus b sine imaginary part x. Now we guess a particular integral. Since this is quadratic, it is x squared plus something x plus 0x plus a constant. So we also have to guess our particular integral as ax squared plus bx plus c. Then we look for a, b, and c. We differentiate the first time, dy dx, and substitute here. And then we differentiate d squared y dx squared and substitute here. So we should have this equation. And then we move on. We rearrange it so that it is quadratic as well. Something x squared plus something x plus a constant equals something on that side. And then we equate coefficient. The coefficient of x squared here is 5a. And on the right hand side is 1. So 5a should be equal to 1. The coefficient of x here is 4a plus 5b. And the coefficient of x here is 0. So 4a plus 5b should be 0. And the constant term should be that. The constant term on this side is plus 4. So 2a plus 2b plus 5c should be 4. These three equations have three unknowns, so we can solve them to get a, that, b, that, and c, that. And so our particular integral will be that. And then, so our general solution should be the sum of the complementary function and the particular integral. But is this all done? No, it's not yet done. We still need to look for a and b. Why we need to look for a and b? Because we are given the boundary conditions here. So we must look for those specific values of a and b. So we will come here. First, we are told that when x is 0, y is 2. So we will have 2 here, and then when x is 0, this is 1. Cos 0 will be 1. Sine 0 is 0, so this will go to 0. This is 0, this is 0. So 2 should be equal to a plus 98/125, and so you can look for a. And secondly, we will differentiate this dy dx, and then we take when x is 0, dy dx is also 0. We will use that to look for b, and then we will state the final solution. Okay. So here is the procedure here. So we look for A and B, and then we state the final solution. Example 4. Solve this equation. We write down the auxiliary equation, m squared minus 9 equals 0. So we have m equal plus or minus 3. So our complementary function is a e raised to the power negative 3 plus b e raised to the power 3. And then since this one is since f of x here is an exponential function, we also have to state our particular integral to be exponential. And then we differentiate it twice and substitute in the original equation. And then we equate coefficients to get our value for a. So we get a as negative 2 over 5. So our particular integral will be negative 2 over 5 e raised to the power x 2x. And our general solution will be the sum of the complementary function plus the particular integral, which is that. Last example. In this case, the only difference is that f of x is changing. So the procedure will be exactly the same. We write down our auxiliary equation, m squared plus m minus 6 equals 0. And then we solve our auxiliary equation. We get m as negative 3 and 2. So our complementary function is a e raised to the power negative 3x plus b e raised to the power 2x. And then since this is a cosine function, our particular integral will be a cos 2x plus b sine 2x, since we have cos 2x here. Then we differentiate it 2 times and substitute in the original equation. And we get that equation. Then we equate the coefficients. The coefficient of cos 2x should be the coefficient of cos 2x here, which is that. And the coefficient of sine 2x should be the same as the coefficient of sine 2x, which is 0 on that side. And so we can get a and b. So our particular integral becomes that. And then our general solution will be the sum of the complementary function and the particular integral. Okay, that is it. Thank you.